Okay, let's start. Uh, First of all, hi all. This lecture series for refreshing your mathematical uh, knowledge about the calculus before starting to the semester. Um, I hope it will be useful for you. The lecture series, the first part of the lecture series is consists of functions, limits, and series. We start with the preliminaries. Um, Here is the some sets, number sets we need to cover. The first one, actually natural numbers. I am not starting with the real numbers because it's cover all the below number sets. Number sets are the positive integers, namely the numbers 1, 2, 3, 4, and so on. Um, a more general version of a natural number is integers. These are the negative and positive um, integers and zero. Uh, and if we give an example, some example, it's 0, plus 1, 2, 3, and -1, -5, etc. Rational numbers are the fractions that written as uh, I can written as n over n. We have a numerator and denominator. Here is the important rule is the n has to be not equal to 0. And then we have the irrational numbers. These are the numbers that the decimal part has to be uh, does not have a pattern, and the real numbers that covers all the natural numbers, integers, and rational and irrational numbers called real numbers. As you can see here, it is natural numbers. It can be natural numbers or integers, and rational numbers. It covers negative and positive numbers, and also the irrational numbers. As you can see here, there is no pattern in the first 6 decimal of the 6 digits of the decimal. It does not repeat itself, and we say that it's an irrational number. And also some additional examples for the irrational numbers. We also we mentioned about the second root of the 3, and also we have the square root of the 5, which is 2.236067. It also does not have a pattern in its digits. And also we have a famous number, which is P, that's using in the mathematics, mostly in the geometry. It also does not have a pattern in its decimal part. The digits not repeat itself. Therefore, we cannot create the number as an fraction, an rational number. And also we have another famous number, Euler's number, which is also does not repeat in the decimal part, as you can see here. And then we have the intervals. intervals also mostly used in the mathematics. It's a subset of the real line, which is called an interval. If this contains at least two numbers and also contains all real numbers between any two of its elements, we call it intervals. For example, we can define an interval which is x greater than 6. It's a great sign interval. It contains the numbers that's greater than 6, all the numbers. And also we have some type of sets. The first one is open sets. Open sets are the intervals that the boundary points are not contained by the interval, which is not the notation for this purpose is this. The difference is when you contain the boundary B or A, you need to use an inequality sign and a straight line above this sign has to be it is the appropriate notation for this. This is it means in this case A and B are not involved in this interval, but the other elements, all the elements are involved in the open sets. And we symbolize it with the bracket. Okay, and it is in the figure and is an open ball on the boundary points, and the rest of the between A and B, all the values are in the our set. And then we have the closed sets. Closed sets symbolized as like this. It is different from the open sets, and it is donated by the straight line and the inequality signs. And when we interpret it or illustrate it in the figure, it has to be the balls with not empty, it's had to be filled balls in the boundaries, and the points between A and B are involved in the interval. We call it closed interval. In order to create a closed set, the 2 boundary points has to be in the our set. If one is open and the second one is closed, we say that it's an half open set. The definitions all similar, but we can talk about the definition. It defines all the real numbers x from A to B. For this case, A in the our interval, B is not involved in our interval. Therefore, we just not fill the B. We need to fill the A, and all the values between A and B has to be involved in the interval. We can illustrate it like this. The suitable interpretation for this A in the X and B is not involved in the X, therefore we denoted it as like this. It can be reverse. If you don't want to take the a in the interval, you use the bracket, and if you want to involve b in your interval, you use it, and the suitable um, the, the notation for this is this. And also we need to talk about the boundary points, of course. These are the endpoints of the intervals, and we call them boundary points. In those cases, A and B interval, which is A and B are boundaries are open. In this case, the boundary points A and B, and also when those boundaries are closed, they are also boundary points. Actually, it doesn't matter if it is open, if it is closed. They are all the the endpoints of the boundaries. Uh, the endpoint of the intervals are our boundary points, and also we have the finite and infinite intervals. The examples that we have mentioned about are called finite intervals because they ended up a point which is not an infinity. Um, this is start with A and finish with the B, as like the others. But in this case, we have a interval which is start with A, which is not involved in the our interval, and it ended up with infinity, and also infinity to infinity, which is there has to be a minus, are infinite intervals. And also we can illustrate the interval like this. It starts with the A, which is not involved in the our interval. Therefore, this is an empty boundary, and it goes to the infinity. And also we have the minus infinity and the infinity interval. It's an also infinite interval, and we illustrate it an as like this, as you can see here. It goes minus infinity and also plus infinity. We already finished our preliminaries. We can go to the functions. Functions also mostly used in calculus. Therefore, we need to refresh those information about functions. Basically, a function is a relationship between two things in which the numerical values of one thing in some way depends on the value of the other. We say that a quantity y is a function of some other quantity x if the value of y is determined by the value of x. If f denotes the function, then we indicate the dependence of y on x by means of formula y equal to f of x. It's actually an mapping, or it's an monitoring mechanism. It's monitor or maps the x values to y values by using an mechanism f here. The set of x that we give or values to the f called the domain of the function it's a set of numbers to which the function can be applied. That is the set of numbers that are assigned to the independent variable. We call the x the independent variable, and we call the y the dependent variable. You can think of like the value of y depends on the x. Therefore, we say that y is dependent to the x. We call it, therefore, y is dependent. X called independent variable represents an input value from the domain of f, and y. The dependent variable represents the corresponding output from f of x in the range of f. The range of a function is the set of numbers that function associated with the numbers in the domain. We call the set of x domain, and the mirroring set, which is which is created by the f itself, the set created by f. We say that it's a range. So we input x, our input here. Let me give this input to the f. From the domain set. F mirrored the x to the range set. It is the mapping from domain to the range, actually. We say that simply mechanism of the function. And also we can define it mathematically. A function f is a rule that assigns to each element x in a set D, which is domain, exactly one element called fx in a set R. It has to be assigned just one element to the range of f. It is the definition of the function. We have some examples with illustrations. We have a function, the second power of x. This is our domain, and this is our range. The illustration and the domain and range sets are not how can I say? They are not matched because it's continuous. These are discrete. Therefore, this is not exactly the appropriate illustration for this. But you can think as a. It starts with actually you can think of it. Domain is the real number, and the range set is the positive real number. And also 0. When we choose x to be 0, our function f of x map its 0 to 0, because when you put the 0 value here, the second power of 0 gives the 0. Therefore, it's corresponding to 0 to 0. And also we have 1. When you choose x to be 1, the second power of the 1 gives you to 1. It can be seen here. It's corresponding to the 1. And also we can choose whatever we want. It could be -1 as well. If you choose x to be -1, the corresponding value for the y-axis is the 1, because you take the second power of the x. And we have second figure, for this one, we use another function. We will mention about deeper insights about the function. But before that, I want to give some illustrations about the functions. And in here, 1, 2, 3 is our domain, and the rest of the integer. It seems like it's just integers, but in the figure, all the real numbers is in the domain actually. And if you use the function and choose 1 for the x, it's give you the 1, and its values something like this. And we have the second value and 2. If you take the second root of the 2, it approximately gives you 1.42, I guess. Something like around this, yes. It's around this. It has, I think it's 1.42 or 1. And we have the square root of the 3 when we choose x to be 3. And also it has to be 1.721, I guess. It's around 1.721. Okay, this is the similar. Again, this is our domain, this is our range. We put those domain values to the f. It maps to the values to the range set. And the illustration for this purpose is like this. When actually you can see here, we will talk about this function in the series and the limits, I guess. When you take the values, which is smaller to 1, it's getting bigger when you go to the 0. And it gets smaller when you pass the 1. As goes to the infinity, it goes to 0. We will talk about in the limit and the series and sequences part. The illustration for this function, 1 over x, is this. Let's pass to some essential function types. The first function is the simplest one, which is the constant function, f of x equal to 2. Whatever you choose your x value to be, the output of your function does not change with the x. It gives the same output all the time. And we have the identity function. The identity function is like whatever value of x, it gives the same thing. If you choose x to be 3, it gives you the same. Actually, in this case, y and x are all the time equal to each other. And we have a signum function. Signum function gives you if the value of x is positive, +1. If the x value is smaller than 0, it gives you -1. And also we have the absolute value function. In the absolute value function, if I know that these are as simple functions, but sometimes we can forget about even the simple functions in our mathematical information knowledge. Therefore, I need to check that all the function types are refreshed. In this absolute value function, if your x is greater than 0, it gives you the same. If your x is smaller than 0, it gives you the 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 value that the same value, but it's multiplied by the minus or -1. It actually mapping a negative values to the positive ones. And also we have the root function. And if we don't define the number here, the degree of the root, it is assumed as 2. Otherwise, we defined it. If it is second degree of root, we wrote it here 3. And we have the exponential or power function. In here we just take the second power of the x, and here is the third power of the x. Some other type of function, increasing and decreasing functions. Here is the informal definition. No, not informal definition. Suppose that the function f is defined on an interval I, and that xi, x1, and x2 are 2 points of I. If f of x2 is greater than f of x1, whenever x2 greater than x1, we say that f is an increasing function on I set interval. And if f of x2 smaller than f of x1, whenever x2 it has to be the reverse. I will fix this after the lecture. It has to be the otherwise. X2 smaller than x1, we say that f is decreasing on I. And also we have the piecewise defined function. It is the function take the different values for different intervals. As you can see here, on different parts of the domain, it takes the different functions. In here, we have the if x smaller than and equal to 0, the function is turned out to be absolute value of x. If x is greater than 0, our functions becomes second root of the x. We can create some functions for some special situations. It could be, for example, text question, maybe text example. If your car is much expensive than $1,000, the taxes maybe second power of the x. If it is cheaper than $1,000, it's just the x. It could be. And we have the composite function. The two functions can be combined to form a new function, which is, we can say that g function map the x values to the say y, and the f function maps the y values to the z. And we ended up with a two mapping with using two functions here. G maps x and f maps g of x in here. An example for this, we have a f function which is equal to second power of x, and we have the second function g of x equal to 1 over x. Then we can calculate the f of g of x as like this. We just put g of x value into the f, and we have the f of g of x, which is equal to f of 1 over x. We just 1 over put the 1 over x into f function, and we know that f function is the second power of x. Therefore, it turns out to be 1 over x, second power of the x. And also we have some other types of functions, linear, quadratic, and cubic functions. Linear function can be defined as we have a x here which have the just power of 1. It has to be just the power of 1. The other types cannot be accepted in this form. When the power of x is 1 and it has a coefficient m, it could be anything negative, positive, but it cannot be 0. If you choose it as a 0, it could be a constant function, but it could be also a linear, but not linear function. Our linear function has to consist of a coefficient m and the first power of x, and there could be a constant plus or minus. We call the m here the slope of the line, and we say the b is the y-intercept or just intercept, and its general name of these type of function called 1-degree polynomial. And we have here the second degree of polynomial, which is also said quadratic function. We have here the second power of the x. It has to be second power of x. It doesn't matter if it is not, if the first power of x and the intercept values are not involved in this function. The second power of the x has to be in our function. And also we have the third power of the x in our function. Therefore, we say that it's a quadratic function. Some properties which can be also useful for the rest of the lectures. One-to-one property. There is a definition, mathematical definition. A function f is one-to-one if when f of x1 not equal to f of x2, whenever x1 and x2 belong to the domain of f, and x1 not equal to x2 or equivalently, actually, if these and these are satisfied, or these are dissatisfied, we say that the function is one-to-one. It can be explained also in the figure. When you draw a straight line from y to from the one side of the x to the infinity, you need to intercept just just 1 point with the graph of the f function. As you can see here, we just intercept with the graph of f just one time in here, and also here we just intercept with one time, and similar to these points. If there is one opposite example for that, what I mean with this, if it is connect 2 points at the same time, a line connects with the 2 point in the graph. There, in such a scenario, we say that it's not a one-to-one function. In the blog, we have an example for this. And one-to-one means also a function has a unique solution for solution x for every given y. There has to be a unique solution for every x in our range. As you can see here in our second illustration, if you draw a line, we have 2 points connected with our curve here. Therefore, we cannot say it's a one-to-one function, but it is a one-to-one function. Inverse function. Taking the inverse of a function, we can create a reverse images as f of -1 of y equal to x. It's a reverse image, reverse mapping. Also, it becomes a function of y and x determined by y. There is a mathematical definition also. If f is 1-to-1, then it has an inverse function, f -1. This, by the way, this is not the -1th power of the f. It's symbolized for the inverse of the function. The value of inverse of f of x is the unique number y in the domain of f, for which f of y equal to x. Thus, we can denote it like this. The notation is called here the if and only if. If y equal to inverse of f of x, if and only if x equal to f of y here. And the reverse case also applies to the same output. We have the onto function, a function f, which is a to the b, is onto if for each b, which is in the b, capital B, there is at least one a in the a with f of a equal to b. An example for not onto function is we have a function of f and its domain is the natural numbers and its range is the again natural number. As you know, natural numbers consist of the positive integer number, but all the positive integer numbers, when our function is 2 times x, we cannot say that the function is onto, because when we choose one here in the domain function and put it the x in here, it projects the 1 to the 2, and it calls the range set to be there is a one unmatched element in our range set. And because the, the value of 1 is not matched with the 1 or another values in our domain set. Therefore, it's not onto. But we can say that if it is not 2 times x, just x, if it could be the x, if it is were, if it was an x, in such a scenario, it could be, it will be the onto function. Bijection, it just f, if f is both onto and one-to-one, then it is called as bijection. It's actually if f function is satisfies all the conditions of onto and one-to-one properties, we call it bijection function. Okay, we have the limit and the continuity in the next chapter. We can start with the definition of limits. The informal definition of the limit is as x gets closer and closer to a from the left and the right side, and f of x gets closer and closer to a value of b. And what do we mean here is that when we getting close to the a value from left and right side, the f function has to map the a value to the b value, and it has to be also get closer to the b. And we will talk about the getting closer case in an illustration. We have here the very simple example. The limit of f of x on the point 1 is equal to 1 because we just one value here, the fourth power of 1 minus 4 times third power of x in 1 and plus 4 times second power of 1, which gives us to 1 minus 4 plus 4, and the minus and positive 4 cancel out each other, and our f function comes equal to the 1. And we can talk about it in this figure. This is the illustration of our fixed function. I can zoom in for a clearer understanding. When we approach to the 1 value in the x-axis, as you can see here, our from the right hand side, as we can as we approach to 1, we in the projection we actually approaching to the 1, and from the left hand side we are approaching to 1 from the left hand side. In the x-axis we approaching to 1 also in the projection in the range. Therefore our limit on 1 is equal to 1 in the projected version of the f function, then its mathematical definition, the mathematical definition of limit is, and it's denoted like this: limit of f of x, x goes to the a, equal to L. If and only if, for any given positive number, epsilon, we call it epsilon here. Sometimes I can forget the names of these Greek letters. However, arbitrarily small positive number, epsilon, we can choose here to approach to the limit that exists a positive number delta. This is actually the projection version of delta. You can think of as when you take the delta values, the image under the f function, it's projects the delta value to the epsilon, and the conditions for this arbitrarily small value of delta, and this is the point that we want to check the limit is exist here, which is a point, and the image that's under a or functions gives us the L. This is the projected value of the f function. Therefore, it's the limit of the f getting closer to the L. When we're closer to the a in the x-axis, it's getting closer to the L. Between the interval epsilon, in here the between the minus and plus delta. And also we have another example and illustration for that. We have a function x minus 1 over third power of x minus 1 in here. And as you can see here, it is not defined when the x is equal to 1. But it does not matter from the definition of the limit, because limit considers close values to 1, not equal to 1. It actually does not matter when you, as you know, when you extend the third power of x minus 1 to and write it like the common factor of x minus 1, the factors, the terms are cancel out each other, and it gives the above illustration. Okay. In here we have some results of some theorems. Limits of a constant function. It is the same as the function case. If it's a constant, it doesn't matter if you choose whenever it is the x values changing, it's equal to c. And we have the multiplication with a constant. And for this, we assume that limit of f of x goes to a is equal to L, and the limit of g is equal to m. If you multiply by f function with a c, and the limit goes to a, it's equal to c times limit of f of x goes to a, and it's equal to c times L. We already talked about that. It's an assumption. And then we summation and subtraction of two functions. Limits of f plus or minus, it doesn't matter. G of x goes to a, it's equal to L plus or minus M, and we have some condition for multiplication of the two functions. Limits of f times g of x, which is x goes to a, can be written as the two distinct limits, which is limit of f and limit of g, which is equal to L times m. And we have the division of two functions, limit of division, and it is very similar to the multiplication. F over g, limit of f over g, can be written as limit of f and over limit g, which is equal to L over m, and we already know that m does not equal to 0. Taking root of the function in here, you can just take out the root to the outside of the limit, and we can write it as nth root of the L if this is defined and there is not inconsistency. Okay.